All right, welcome to another fabulous day in Calculus 3. We're going to wrap up the divergence theorem today. So if you recall, last time we looked at this thing called the divergence theorem. So what do you use it for, and what's it, what's it all good for? So if you're being asked to find overall flux through a closed surface, instead of doing more than one flux integral, this is known as a flux integral, you can do a single triple integral, which is nice. And usually it's easier. So the integrand of that triple integral that will help you to calculate the overall flux contains the divergence of the vector field. So you already know how to do that. So we did a few examples last time. So let's do some more examples. So the example I want to start with today is example 4. And example 4 is finding the total flux through a parallelepiped. What the heck is a parallelepiped? Well, it's kind of fancy for a rectangular box, but it could be a box that's a little bit sheared at an angle too. But I think this one is a nice rectangular box, nothing special about it. So let's just take a look at the way they're giving it to us. So they're telling us that this parallelepiped here is bounded by the coordinate planes. Immediately, that should tell you we're in the first octant. So those are going to be some of the sides of the solid. And then it's also bounded by 3 planes. Well, a plane x equals 1, which is the vertical plane that cuts through the x-axis at the 1. So that's going to be like one of the sides. And then the plane y equals 2, so that's going to be another vertical, should maybe do it more like this, a vertical plane. So that's the plane y equals 2. And then the third plane, z equals 3, is going to be basically the top of the box. Okay, so I hope you can envision here, we've got a rectangular box bounded by the coordinate planes and then these 3 planes. Fine. They're giving us a vector field. They want us to use the divergence theorem to find the flux of the vector field over the entire surface. This is a closed surface. It's got a lot of sides though. If we weren't allowed to use the divergence theorem, how many separate flux integrals would we have to do and then add the results? Does anybody see how many surfaces total make up this solid?
6.
Good. Yeah, 6. You'd have to do 6 flux integrals. Oh man, that'd be annoying. But instead, we'll just do one big triple integral. So we're going to go flux is equal to the triple integral over this solid, and we'll take the divergence of f. Okay, so we have m, n, and p. So let's go ahead and get dm dx plus dn dy plus dp dz, because that's what divergence is, right? So taking the partial of 2e to the negative x, z, with respect to x, you're going to need to use the exponential rule when you differentiate. So you're going to have a negative e to the negative x. And so I'll just put the negative out in front. So that partial will be negative 2e to the negative xz plus dnby, the derivative of xy squared with respect to y. I think that's going to be 2xy plus the partial of z cubed with respect to z, 3z squared. Okay. And then the volume element is going to be my personal favorite order, dz, dy, dx, rectangular coordinates, volume element. So since I picked this order of integration, we got to be careful when we put the limits on the integrals. Now, because this is a rectangular box, all of the limits will be constant, which is kind of nice. So we see that z is going from z equals 0, which is the xy plane, up to the top of the box, z equals 3. Y is going from y equals 0 to y equals 2. And then x is going from x equals 0 to x equals 1. There we go. And now we're ready to start integrating. And of course, I'm going to run out of room. So if we integrate with respect to z first, we'll get negative e to the negative x z squared plus 2xyz plus z cubed, and we're evaluating that going between 0 and 3. So the 0 will, everything will go to 0. That doesn't always happen, and that's one of the reasons why I like putting this particular example in my lecture notes, because it's a common student error we're about to see, not yet. So when I plug in the 3, everywhere I see a z, I'm going to end up with, let's see, negative 9 e to the negative x plus 6xy plus, and then 3 cubed is 27. Okay, so now we're getting closer. Let's integrate with respect to y next. Okay. I'm going to get negative 9 e to the negative xy plus 3xy squared plus 27y. Ooh, okay, let's evaluate going between 0 and 2. That's a dx still left. Now, when we plug in the 0, everything will go to 0. So we're just not going to bother. So we'll get what? We'll get negative 9 times 2, negative 18 e to the negative x plus 3 times 2 squared is 12. 12x plus 27 times 2 is 54. Okay, now this is an easy integral, but be careful. I'm going to show you the student pitfall. After we integrate, we'll get 18 e to the negative x plus 6x squared plus 54x, and we're going to evaluate between 0 and 1. The common student error right now, I just want to point it out because I don't want this happening to you, silly mistakes, you know, on the midterm coming up for the final. When you plug in 0, a lot of times it's true that you don't need to bother because, hey, you know, the entire integrand is going to go to 0. This is not the case for this problem. Watch closely. We'll first substitute a 1 in place of x. Okay, that's pretty easy. Minus, to be careful, do you see where 0 is not going to go to the 0 when we substitute in a 0? So this right here is not equal to 0. So that's why you got to be careful. So my final answer is going to be what? Ooh, minus 18. We've got 60 minus 18. I believe that's 42. So our final answer after we add all these constants together is going to be 42. So there's your exact answer. Yay, and we're done. And since that's a positive number, we have what's called a source. That's where your leprechaun is inside your solid, you know, spitting out more water. So more water is flowing out of the surface than flowing back in. This is approximately, if you whipped out a calculator, 48.62. And we're done with that example. So there is an example of finding total flux using the divergence theorem. Oops, we end up with this thing was a source, and we needed rectangular coordinates. Fine. So that example is done. So this next example is sort of a double whammy that I want you to see for yourself so you can have full enlightenment. First off, check out this weird notation. And normally what our flux integrals look like is they look like a double integral with an S, and then you see f dot n ds like this. But this one has a different look because I in another textbook or a different class. You'll see it looks like there's only a single integral symbol. It's like, wait a minute, I thought flux integrals are double integrals. They are. However, mathematicians and a lot of times physicists get kind of lazy. So you may see them put a single integral symbol, but there's an S below. So everybody who's in the know knows that that means there really is a double integral. Okay, so don't be fooled by this single integral symbol. The other extra that you'll see here is that circle around the symbol, which we've seen before when we studied greens, remember? that meant a closed curve when we were doing greens. Well, when you see it around this with an S, it means closed surface. Means closed surface, which you need. That's one of the criteria if you're going to use the divergence theorem. Oh, okay. And then you have a lowercase n. All right, that's just different. And then you have a subscript out because that's typical for using the divergence theorem. They always have those orientation vectors directed outward from the solid. So just a little different notation. Just want you to be okay with it. So let's take a look at this and see why it's different. They're telling us that the solid is a sphere. Ooh, and that's a nice sphere that everybody should recognize, centered at the origin of radius 2. Fine. So what's the big deal? Well, the big deal is you'll see in a moment, and I think it'll come to you. But first, I'd like to find the divergence. So we're given the vector field. I'm just going to copy it down here quickly. We had 2x cubed, 2y cubed, 2z cubed. So then the divergence of f is going to be dm dx. So that's going to look like what? 6x squared plus dn dy, 6y squared, plus dp dz, 6z squared. So there's your divergence. So the total flux is going to be equal to the triple integral over the solid, which happens to be a sphere. And we have the divergence of f in there. And we just got the divergence of f. So we're going to have 6x squared plus 6y squared plus 6z squared. Okay, fine. What's the big deal? Well, I hope you remember that when you have a triple integral and you're integrating over a sphere, what do we usually convert to? Anybody remember?
Polar.
Close. Triple integral.
Spherical.
Spherical. You're going to need spherical coordinates. So we're going to convert. Yeah. So what do we know about our sphere? Well, the sphere, they told us here, was x squared plus y squared plus z squared equals 4. So remember, with spherical, you have to worry about rho, theta, and phi. And so let's figure out all the ranges or limits, if you will, for these 3 variables in your spherical coordinate system. So rho, it turns out, is going to go from 0 to the radius of our sphere, which is 2. Theta is going to be the theta we all know and love in the xy plane, going to take on the full revolution, 0 to 2 pi. And what do we do for phi if we're doing a sphere centered at the origin of radius 2? Does anybody remember what phi would be?
Pi.
Okay, that's the upper limit. Good. And what would be the lower limit?
0.
Good. So that's going to be what we have for all of our coordinates for the rho, theta, phi spherical. Great. Now, what about this integrand? Oh, shoot, we got to convert that. So what I'm going to do is I'm going to factor out a 6, and let's see if we remember, what do we replace x squared plus y squared with plus z squared?
Is it rho square?
Good. Excellent. So we're going to have 6 rho squared. Now, what about this volume element? Remember that weird volume element for spherical? What does it become? I know it's weird.
Rho squared sine phi.
D rho, d phi, d theta. We usually do typically in that order. So we're almost ready to go. Let's just put our limits on there. Theta went from 0 to 2 pi. Phi went from 0 to pi. And rho went from 0 to 2. Boom, there we have it. That's half the battle, setting it up. So let's combine our powers of rho into one big old power of rho, and then we can integrate with respect to rho to start. and I'm going to pull the 6 outside. So the antiderivative of rho to the 4th is rho to the 5th over 5. And the sine phi is there. It's just a multiple. We still have to do 2 more integrals. And after we evaluate rho to the 5th over 5 from 0 to 2, we're going to get 32/5. Let's pull that out in front. So now we just have to do sine phi with respect to phi. And that's easy because it's minus cos. And this right here, I think, is 192/5. So we're going to have minus cos phi going from 0 to pi. You got to be careful here, because cos of 0 is not 0. Oops, what the heck am I doing? So cos of 0 is 1. So here we have a minus 1, which is plus 1. And cosine of pi is negative 1, but we have a minus minus there. So this is really going to end up being 1 plus 1, which is 2. Hey, great. Let's just pull that multiple out in front and multiply it with our 192/5. And now we just have to worry about integrating 1 with respect to theta. That's easy peasy. That's just theta. And then we're going to go from 0 to 2 pi. And so then we're just going to end up with a factor of 2 pi. Final answer, 768 pi fifths. And that's going to end up being a source because this is a positive number. So total flux through our sphere, 768 pi fifths. And that was another example of using the divergence theorem. So what was the whole point of this problem? A couple things. I wanted to introduce some alternative notation to you. And this problem, one of the big things was spherical coordinates. Yeah. Now remember last lecture, I did an example where we used the divergence theorem with cylindrical coordinates. So there's 3 possibilities now when you're doing divergence theorem. You could stay in the rectangular coordinate system. You might find you need to convert to cylindrical coordinates, or you might need to convert to spherical coordinates. So be prepared for any of those 3 possibilities on your homeworks as well as your exams. Okay? Now, the last couple problems here for divergence theorem, I like to show you because they're great. They really make a point here. So example 6, suppose a vector field F is given by F equals that differential operator cross product with B. Now remember, that means the same as curl of B, where B is some other vector field. So remember, curl of a vector field is itself a vector field. So this vector field F is a vector field. He's just the vector field given by taking the curl of some other vector field named B. Okay, so what? Well, our physics brethren call this kind of vector field a solenoidal field because it's the curl of another field. So solenoidal fields are kind of interesting. Watch closely. Why? Because it's going to turn out where the total flux for this vector field over any closed surface is always equal to 0 no matter what. And they're not even telling us what B or F are. I mean, they're like, hey, just do the problem. Oh, are we missing any information? No, it turns out they gave you all the information we need. Okay, fine. So total flux, which we could do using one of those flux integrals. I'll just be kind of weird and do one of those weird alternative notations. And then I'm going to show you another new notation. What if you see a single integral with a V underneath? What does that mean? That means it's a triple integral. And then I'm putting a circle around it means closed surface. And so remember, if we're going to use the divergence theorem to figure out total flux over any surface, and we'll just call that surface V, you're going to need to take the divergence of F. But that is going to be the divergence of the curl of B. But we went over the Biggie theorem a couple of lectures ago, when we learned that the divergence of the curl of a vector field is equal to 0. So what does that mean? This right here is 0. So our total flux is 0 over that surface, which is going to be a big fat 0 for all closed surfaces. So that's kind of interesting. I wanted you to see that, because who knows, it may be a problem that you'll have on one of your physics tests, and boom, you'll have it done, because you already have seen this little mini proof. Congratulations. Or it could be a true false question. Great true false question. Okay, the last problem I'm going to do here, we're going to use some of our knowledge using the divergence theorem with a little trick to find the flux through a surface that is not closed. Now, this problem comes courtesy of Dr. Vallone of blessed memory. I told you about him. So what up with this? So we're going to consider the northern hemisphere, the upper hemisphere, of a sphere of radius A as our surface. So if I were to graph this, it's just, you know, some radius A, they're not telling us. And the northern hemisphere is an upper hemisphere. This is not a closed solid because it's not containing, you know, a full sphere or anything. So they're giving us a vector field, and they want us to consider the flux through the surface that isn't closed. It's just the capping surface here only. So what we're going to do, this is our trick. We're going to close off this northern hemisphere by giving it a base plate. Here's our base. We're going to close it off. So we're going to make it closed. Okay. So what we're going to do now is we're going to find the full-blown flux through this closed surface, which involves two surfaces total, the hemisphere part and then the base plate. And then we're going to subtract off the flux from that bottom surface, from the base plate. So what are we trying to say? What we're trying to say is that the flux through the northern hemisphere is going to be equal to the total flux through the closed surface when we gave it a base plate, and then we'll subtract off the flux through the base plate. And that will be, and then we'll finally get our answer. So this is the goal, but why are we not doing the goal? Because it turns out it's kind of hard to get that. So what I claim is doable is we're going to do this. This is easy because we'll use the divergence theorem. And this is easy because we'll do an easy flux integral just through the base plate. Okay? So this divergence theorem total flux, we're going to do, you know, it'll have this look to it. And this easy flux integral through the base plate will look like this. So what I like finishing with this problem because it's sort of a do everything kind of thing when it comes to flux. And it makes kind of a nice little trick problem. Okay. So let's do this first. So if we had this full-blown closed surface that's got, you know, it's all closed off because we gave it a base plate, we're going to go get the divergence. Okay, so what is the divergence? So they gave us the vector field. Well, dm dx is 1 plus dn dy, ooh, that's nice, is also 1. And dp dz is also a 1. Oh, brilliant. So what do we have here? That's just a 3 for divergence as a constant. That doesn't always happen. But when it does, we're always grateful. And then what? This triple integral just has a 1 as its integrand. So this represents volume from what we learned about triple integrals in our previous module. The volume of what? Of this closed surface. Well, what is the closed surface? It's a half of a sphere. And we just use our knowledge of finding the volume of a sphere. Now, I don't know if you guys know maybe by memory, but I highly recommend you put this on your sheet of notes for the final, is the volume of a sphere is 4/3 pi r cubed. So half of a sphere's volume will be half 4/3 pi r cubed, okay? So the radius that we have, and then you can 4/6, you can reduce, right? The radius, we don't know what the radius is. It's just some variable a. So it's going to be, when all is said and done, the volume will be 2/3 pi a cubed. But then don't forget this 3 over here. So what we're going to do is we're going to have 3 times this 2/3 pi a cubed. That's the volume. And then we can reduce because the 3's cancel. And then we get 2 pi a cubed. Let's save this for later. And why is that important? Because remember, the strategy for the problem is we're going to get the total flux through the closed surface, which we just got. It's 2 pi a cubed. And we're going to subtract off the flux that goes through the base plate. So that's next. So let's just get the flux that goes through the base plate. We have to do a regular flux integral. Whoops. I should put S's. Let's do S. Flux integral, the basic flux integral looks like this. You're going to turn it into a regular integral by taking the dot product of two things here. Ooh. So who are you taking the dot product of? F, which was what? They gave it to us here, x, y, z plus 1. We'll work on this in a second. And then n. Now, n is a normal vector directed outward. Now, if you look at this base, the base is simply given by z equals 0 because, you know, it's just in the xy plane. So a normal vector to that base plate would be a vector pointing straight down, you know, so you're going to basically, if you do negative, if this is your g, negative gx, negative gy, -1, because you need it direct. Oops, I should do positive gx, pardon. We're doing an oriented downward normal vector. So when you take the partial of that with respect to x, well, I get a 0. And the partial of that with respect to y, I get a 0. And a -1. I hope you can see that orienting this base plate with a downward normal vector n makes sense because it is oriented outward. Okay. Now, remember, you're not allowed to have z's in a double integral. So what do you have to replace the z with? Uh-oh. Remember that that base plate has z equals 0 because that's what z is doing in the xy plane. So you'll just put a 0 there. Ooh, that makes it easy. And then what's your region R? Well, if you look at the trace that this solid makes in the xy plane, your R is going to look like a circle centered at the origin of radius A. Okay, fine. So let's worry about that in a moment. Let's first do the dot product, shall we? So you're going to have x times 0 plus, oh, this is easy, y times 0, okay, plus 1 times -1 dA. Oh, okay, that's just going to be, you know, 0 plus 0 plus -1, and I'll pull the -1 out in front because it's just a multiple. Then what? We're going to use our knowledge of double integrals. Double integrals that have an integrand of 1 represents area. Well, area of what? Area of the circle. Right there. And we all know that circles have areas pi r squared. And so for us, we're going to have pi a squared because that's our radius. So negative pi a squared is the flux that's going through the base plate. Now what? We're ready for the final answer. So the flux through the northern hemisphere only is going to be equal to the flux if the solid were completely closed, which is 2 pi a cubed, plus, or I should say, sorry, minus, we're subtracting off the base plate. So a minus minus is a plus. So our final answer, I know this is kind of weird, but this is the exact answer. And this is a positive, so it would be a source. The final answer is the total flux through the northern hemisphere only is 2 pi a cubed plus pi a squared. And we're done with that example. Now, folks, I am not going to give you an example like this on the midterm or the final. Well, then why'd you do it? Because a lot of it gives the culmination of flux and the idea of closed surfaces and flux integrals. And if you're integrating a double integral with a 1, you better know that's area, because that happens a lot in physics. And if you're doing a triple integral with a 1 in the integrand, that represents volume. All of these ideas and concepts and connections come to play in this big old example here. And that's why I like to include it in my lecture notes. So if you understood it, congratulations. And that concludes the divergence theorem. Yay!